Welcome back to episode 7 of our documentary explainer series, Inside Time series. For decades, banks, governments, manufacturers, retail giants, and economists have all relied on one central forecasting algorithm to predict the future. The mystery we're unpacking today is simply this: how did one single algorithm become the absolute gold standard for forecasting? What exactly made ARIMA so powerful?
Well, to understand that, let's take a quick second to recap our journey so far. Over our past few explorations, we've uncovered hidden trends by smoothing out data with moving averages. We've learned how to look at past values using auto-regression. We've even seen how to learn from past forecasting errors using moving average models. And of course, we discovered that crucial concept of stationarity, the idea that our data really needs a stable mean and variance before we can actually accurately predict it.
Okay, so here we are. Welcome to the climax of our classical forecasting journey. Today, we're going to reveal a pretty big secret. ARIMA isn't actually some brand new, entirely separate algorithm. Instead, it's this brilliant, elegant synthesis of literally every single concept we've explored so far, all rolled into one highly effective framework. So here's our roadmap for this explainer. We're going to cover the forecasting legend itself, decode the 3 letters, look inside the algorithm, see ARIMA in the real world, and finally, talk about why ARIMA wasn't actually the end of the line. We're going to treat this famous algorithm not as some monolithic, scary math equation, but as a really intuitive 5-part recipe.
All right, let's jump right into part 1, the forecasting legend and how it became a universal standard.
The most crucial thing to grasp here is that ARIMA absolutely dominates because it perfectly combines our 3 foundational forecasting ideas into a single machine. You take auto-regression, you add differencing to handle those non-stationary trends, and then you combine it all with a moving average model. The result? ARIMA, which stands for Auto-Regressive Integrated Moving Average.
That brings us to part 2. Let's actually decode those 3 letters, A, R, I, and M, A.
Notice the really brilliant contrast here between the first and last parts of this model. The AR, or auto-regression component, basically assumes tomorrow is going to be a lot like yesterday. It captures trends and inertia, predicting future values based on a linear combo of past observations. But on the flip side, the MA, or moving average component, adjusts our prediction based on how wrong we were yesterday. It pulls in past forecast errors, which allows the model to correct for sudden, short-lived shocks that the general trend just misses.
Now, to bridge those 2 together, we have the I for integrated. In practical terms, this simply means we apply a differencing filter to our data. Remember our golden rule about stationarity? If your data has a wild upward trend, its mean is changing over time, meaning it's non-stationary. The I component literally subtracts yesterday's value from today's value to strip away that trend, making the whole series stable enough to actually forecast.
And this perfectly illustrates why we so desperately need that differencing step. Take the historical data for the quarterly population of Australia, for example. If you track that, you see a massive, clear upward trend. Our algorithm simply cannot forecast that accurately in its raw, trending form. We absolutely have to use that differencing filter to flatten that upward slope into a stationary horizontal line before the AR and MA components can step in and do their magic.
When engineers are out there actually using this model in the wild, they write it out as ARIMA PDQ. Now, they aren't doing abstract calculus from scratch. They are quite literally just tuning 3 dials. P tells the model exactly how many past values, or lags, to look at. D is the number of differencing operations needed to flatten out the trend. And Q is the number of past errors, or shocks, to factor into that next prediction. Moving on to part 3. Let's take a look inside the algorithm at what we call the Box-Jenkins pipeline.
This procedure is a highly structured, step-by-step pipeline. First up, we take our raw data. Second, we run a stationarity check on it. Third, if that data has a trend, we apply our differencing operations to stabilize things. Fourth, we fit our auto-regressive and moving average models to capture the hidden patterns. And finally, step 5, we generate our forecast. It's a remarkably clean workflow.
But wait, how do we know exactly what numbers to pick for our P and Q parameters in the first place? Well, engineers use visual tools, specifically autocorrelation and partial autocorrelation plots, usually called ACF and PACF. Without getting bogged down in the heavy statistical proofs, you can really just think of these tools as a way to visually see exactly where the data's memory starts to fade out. By checking where the data spikes drop inside certain confidence intervals, an engineer can visually identify exactly how many past values and past errors the model needs to care about.
All right, part 4. Let's see ARIMA in the real world, moving from theory into actual application.
Because it can simultaneously handle unobserved random shocks with the MA component and technical long-term trending with the AR component, ARIMA quickly became the absolute backbone of massive real-world systems. We're talking about deploying it to reliably predict retail demand, inflation, national GDP, crazy stock market movements, electrical grid energy demand, and even healthcare resource planning. It is, without a doubt, an absolute workhorse.
However, to truly understand this model, we have to acknowledge a pretty critical limitation. Because the algorithm relies entirely on an additive combination of immediate past values and past errors, the further out your forecast horizon stretches, the more uncertain your predictions are going to become. It's kind of like walking in a straight line while blindfolded. The more steps you take based solely on your last known position, the more likely you are to drift completely off course.
Which brings us to our 5th and final chapter, why ARIMA wasn't the end of the story and its ultimate blind spot.
I want you to ask yourself, what happens when your data has repeating seasonal patterns? Think about the massive spikes in retail sales every single December during the holidays, or electricity demand completely surging every summer when the air conditioners all kick on. How does an algorithm that only looks at the immediate past, say the last few days or weeks, handle a predictable yearly cycle?
Well, the surprising truth is, standard ARIMA kind of breaks down here. It completely fails to understand that today's data might actually be heavily influenced by what happened exactly 1 year ago. If you're only looking at yesterday's temperature to predict today's, you are going to be completely blindsided when winter suddenly turns into spring.
This single realization is what forced the evolution of classical forecasting. It proved that while ARIMA is an incredibly powerful synthesis of everything we've learned, it definitely wasn't the end of the story. The future isn't just influenced by yesterday. Sometimes it's influenced by last winter.
So next time, in Episode 8, we're going to introduce SARIMA, Seasonal ARIMA, leaving you with the exact tools you need to predict those cyclical mysteries. But until then, I want to leave you with this question. If our most powerful algorithms can only see the future by looking at the past, what happens when tomorrow brings a season we've never even seen before?